ladies and gentlemen, today we're going to learn about electric potential. Now, the equation for electric potential is V is equal to Coulomb's constant K times the charge that we are looking at, all divided by the radius. Now, that's the equation. Before we actually get into what the equation means and what the graphs might look like, it's important to know how we can figure out the electric potential based on one other very important idea, the electric field. All right. Now, I'm going to use this tennis ball as my model for the charge. Now, let's say this is a positive charge. All right. It's officially a positive charge. So we have a positive charge, and this positive charge has an electric field that is shooting out in a 3D fashion. Okay? The electric field lines are pointing at you in a way, and it's just going all over the place. So a very important concept is that the closer you are to the charge, the stronger the field is. The further out you are from the charge, the weaker the field is. Okay, so the closer you are, the stronger it is. The further away, the weaker it is. It's kind of like if you were to think about I don't know, like the sun. Wow, right? So if this is the sun in our solar system, and this sun is massive. It has its own gravitational field. The closest planet, Mercury, okay, is experiencing a greater, it's like really close to it. So the gravitational field that Mercury is in it's really strong, right? And here we are at Earth, like a little bit more away. But here on Earth, we feel the gravitational field when we drop things. Okay. Actually, that was really bad. Let's go back to the sun. All right. So here we have the sun, and the sun has its own gravitational field. And the closer a planet or any celestial object is to the sun, it's going to really feel that gravitational pull. Okay, because it's massive. And the object is super, super close. So Mercury feels a stronger gravitational field than any other planet, especially if we are to compare it to, let's see, are we considering Pluto planet? I guess not. All right, so Neptune, the other furthest one away. So Neptune from the sun is really far away. Now, because Neptune is so far away, the gravitational field that Neptune feels from the sun is a lot weaker than what Mercury might feel from the sun. Okay? And this applies to the electric charges as well. Okay? The closer you are to the electric charge, the stronger the field. Now, I'm going to draw an electric charge here. I'm going to call this a positive charge. This positive charge has an electric field. Now, mind you, this is 3D. Okay? This is a 3D field. It's all around this positive charge. The field goes everywhere. Okay? The electric potential, when drawing it, we have several rules that we follow. Rule 1 is that it has to be perpendicular to the field lines. So what I'm going to do is I'm going to add a couple more field lines to make it a little bit easier for me to draw. So if the radius at that point, I'm going to call that R1. So from here to here is R1, and here to here is R1, 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 R1. So it's the same distance all around the charge. What we know from this equation is that as long as we have the same radius that emanates away from the charge, okay, same radius away from a charge, the electric potential at those points have to all be equal. So when we draw electric potential lines or equipotential lines, we always draw it perpendicular to the field lines. Perpendicular to the field lines. Okay. So at those lines, the voltage is all, I'm going to come up with a number. Let's say 100 volts. All right. Now, if we were to increase the radius, okay, and we are to go away further from the charge, okay, I'm going to call that R2 with my blue marker. Okay, that's R2. This is R2, 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 R2. If all of those points are R2, and they are the same radius away from this positive charge, at those points, it will always have the same voltage. Okay? And so when we draw the equipotential lines, remember, it's always perpendicular to the field lines. Always perpendicular to the field lines. And so we get a very familiar shape. This is what we call a circle. Wow. Now, this is a circle because it's a 2D model. But if we were to go in 3D mode, that means for this positive charge, even if the fields are shooting out in all directions, okay, the equipotential is the same spherically all around. The closer I get, okay, that little cage of my fingers, right? The closer we get, the electric potential is stronger, but the further out we get, all along here, the electric potential gets weaker and weaker the further out we go. Okay? Now, let's say, if we follow the rules, we'll say that the blue line, if the black lines was 100 volts, we can say that this was, like 20 volts. Okay? Now, let's say that the radius is really, really long, like pretty far away from the charge. The electric potential, it gets weaker. It gets weaker like this. Okay? So at the red points, let's say the voltage was just 1 volt, okay? Because it's further out. So all along this red dotted line, it has the same equipotential value, okay, or the same electric potential value. Now this is a 2D model. Another way of looking at this is with a sideways profile. All right. Now with a sideways profile, I'm going to start off with a positive charge because we've been dealing with positive charges. All right, so here we have a positive charge, and we're going to call this point, this axis, that's going to be my R is 0. All right, now, from here, the further out we go, the equipotential lines will look like this. All righty, now, R1, so from here to here, okay, so if the field is shooting out all over the place, all right, like this, pew, 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 right? So the field lines are going all over the place, but I'm going to erase those because those are messy. At R1, okay, at radius 1, this will have an equipotential here, okay? And that point was, I think I said 100 volts. All right. So if we were to have another test charge, and we put that test charge out here, let's call that R2, right? When it's further out from it, the equipotential was in blue. And so all along here, right? And I think, what did I say? Voltage was 20 volts, I believe. I don't know. It's smaller. That's what that really matters. Okay. So all along this radius, right, from here to here, as long as that radius is the same, it doesn't matter what side of the charge that you're on. Okay, so if this is R2, right? Ooh, right? The electric potential is going to be a little bit weaker. And of course, if we go even further out, let's say here it is R3, and at R3, I think we said the voltage was 1 volt, so that means that from here all the way to here, okay, all along this mountain, okay, if we were to imagine this as a mountain, like a 3D mountain, all along the base of the mountain, the potential is 1 volt. Now, you might be thinking to yourself, what is electric potential? What is electric potential? So if we have a positive charge, okay, and we were to get a test charge, and our test charges will always be positive. If we get a positive charge and a positive test charge, what electric potential means is it's the ability for the electric field to do work. Okay, so if we were to replace this positive test charge with another positive charge, okay, the electric field from this positive charge will have a pretty strong effect on this positive charge. So it can do it's going to be doing like a lot of work. It has the ability to do a lot of work. It's going to like shoot it out. Okay, but if we have this positive charge and we put a test charge right here, and the radius is like pretty far away, then this positive test charge is going to be like, the potential is pretty weak. Okay, it's not that big. So what that means is if we were to have a positive charge and we were to put a positive charge here, this positive charge, it's not going to have the biggest effect. It's not going to, the field from this charge is going to really not be able to do much work to this positive charge. Okay, they're going to push each other away, but it's not going to be as much like if they were like super close to each other. Now you might be thinking to yourself, Mr. Lee, what if this is a positive charge and we have a positive test charge here, but instead of replacing it with a positive charge, we replace it with a negative charge? What would happen? Well, the ability to do the work is still the same. Okay? Because this negative charge is so close to this positive charge, it's going to attract it even more. And so it's going to pull it even more. If we were to have this positive charge and this negative charge and it's super far away, it's still going to, it has the ability to do work, but it's going to be a little bit weaker. Okay? It doesn't have as much potential. So what this means in terms of our graphs, okay, if we were to take a look at our equations, V is equal to KQ over R, it shows us that as long as the charge remains a constant charge, the voltage has an inverse relationship with the radius. So if this y-axis is the electric potential voltage, and the x-axis is the radius away from the charge, okay, and this, we'll say that this is about infinity, and we'll say here is 0. The closer you are to the charge, the voltage is super high. Okay? So for a positive charge, it'll be up there. It'll have positive potential. But the further out you go from the charge, like infinity, the voltage approaches 0. It doesn't actually reach 0, it approaches 0. And what we get is this beautiful straight curve. And that's for a positive charge. Okay? And the inverse is true too. So if we have a negative charge, and we're like super close to a negative charge, we have a lot of negative potential. Okay? Now that negative potential, it doesn't mean that it's like bad or evil. It just means that's a negative charge. But the further out you go from the negative charge, it approaches 0. So we get this beautiful curve like that. Yeah. And that's for a negative charge. This shows an inverse relationship. And that's it.